Hi there, in this video I'm going to go through the derivatives of hyperbolic functions. Okay, so let's call this hyperbolic derivatives. Take a red pen, let's underline that. So the first result, so if y equals hyperbolic sine x, dy over dx should give you hyperbolic cos x. Okay, so that's the first result. Now you can prove this result by differentiating the definition of hyperbolic sine. So let me show you what I mean. So in order to prove this result, we need to use the definition of hyperbolic sine. So remember, y is hyperbolic sine x, and that had the definition e to the x minus e to the minus x divided by 2. Okay. Now, if I differentiate this term over here, so remember, if you differentiate e to the x, you're going to get e to the x. But if you differentiate e to the minus x, it's minus e to the minus x. Okay. So in this case, before I differentiate, let me split this and write this as e to the x over 2 minus e to the minus x over 2, which when we differentiate should give us e to the x over 2 plus e to the minus x over 2. And if we take a common denominator of 2, that is e to the x plus e to the minus x. And this, remember, is the definition for hyperbolic cos. Okay, so that is how you would prove that if y equals hyperbolic sine x, dy over dx is hyperbolic cos x. So you would prove that by differentiating the definition. Okay, so number 2, if y equals hyperbolic cos x, dy over dx on we differentiate, we should have hyperbolic sine x. So again, let me just go through this one also. So let's go through the proof of why this happens. So y is equal to hyperbolic cos x. Remember, hyperbolic cos has the definition e to the x plus e to the minus x over 2. And if I separate the terms, I'll have e to the x over 2 plus e to the minus x over 2. Okay, and if I differentiate this, dy over dx should be e to the x over 2 minus e to the minus x over 2. By taking a common denominator of 2, then we're going to have e to the x minus e to the minus x over 2. And as you can see, this is the definition of hyperbolic sine. Okay, I hope you can see that. So let me go through the other derivatives. So over to the reverse side. Number 3, if y equals hyperbolic tan x, dy over dx is hyperbolic sec squared x. Okay, and you can prove this, so I'll let you prove that yourselves using the definition of hyperbolic tan. Number 4, if y is equal to, okay, hyperbolic cosec x, dy over dx is minus hyperbolic cosec hyperbolic cot. Okay. Number 5, if y is equal to hyperbolic sec x, dy over dx is minus hyperbolic sec x hyperbolic tan x. Number 6, if y equals hyperbolic cot x, dy over dx is minus hyperbolic cosec squared x. Okay. So these are the derivatives, so if you want, you can box them or you can highlight them. So these are the derivatives of the hyperbolic functions. Okay. And you can prove these derivatives again by differentiating the definitions. Okay, so I proved the first two, the results for y equals hyperbolic sine and y equals hyperbolic cos, and we've seen how these derivatives come about. Okay, and you could also equally prove these results here. Okay, so you should get these results. Okay, for 3, 4, 5 and 6. I'm going to go through some additional results that I'm going to get using the chain rule. Okay, so in this case, so let me just call this hyperbolic differentiation continued. Okay, so I hope you can see that. Let's underline that. So let me show you how to get some additional results for the derivatives of hyperbolic functions using the chain rule. So for example, let me number them. Number 1, supposing if y equals a hyperbolic sine ux. Okay, so in this case a is a constant, so where a is a constant and ux is a function of x. So a is a constant, ux is a function of x. So let me use the chain rule. So by the chain rule, so remember the rule, dy over dx, that is dy over du times du over dx. Okay, so in one of my videos on differentiation I went through the chain rule. Now y in our case is a hyperbolic sine u, so my u is the shorthand for ux. Okay, so dy over du, so what I'm doing is I'm trying to calculate dy over du here. So when we differentiate hyperbolic sine, in the previous video it's hyperbolic cos, and bearing in mind a is a constant, so if we differentiate a hyperbolic sine u with respect to u, we should get a hyperbolic cos u. Okay, and finally if I replace dy by du with what we have over here, a hyperbolic cos u, therefore dy by dx will be dy over du, which is a hyperbolic cos u, times du over dx. Okay, so that is what you should have when you differentiate a hyperbolic sine u, where a is a constant and ux is a function of x. Okay, what I would say is I don't like to memorize these results, so just learn what this result is trying to say. So the result itself is trying to say you differentiate using the basic result or the standard result. So remember, when you differentiate hyperbolic sine, you get hyperbolic cos, but you need to multiply by d by dx of this term over here. So you always multiply by d by dx of this term over here, and you only use this result, everyone, if a is a constant. So that's important. So only do this when a is a constant. If a is a function of x, you may need to use either the product or quotient rule. Okay, so in the same way, number 2, if y equals a hyperbolic cos ux, so in the same way, let me go through the proof, or let me just go through how this result is found using the same steps. So remember, by chain rule, dy by dx, that is dy over du times du over dx. Okay. Again, let me go through an intermediate calculation just as what I did previously here. So y in this case is a hyperbolic cos u. So remember, when you differentiate, and again a is a constant, when you differentiate hyperbolic cos, so this should be hyperbolic cos, you're going to get hyperbolic sine. So you're going to get a hyperbolic sine u. Okay. Also bearing in mind u is our shorthand for ux. So if I replace finally dy over du back into our chain rule result, dy by dx will be dy over du, which is a hyperbolic sine u multiplied by du over dx. Okay, so once again, don't memorize these results, so think about it. When you differentiate a hyperbolic cos u, in this case, if a is a constant, the derivative will be a hyperbolic sine u. So when you differentiate cos, you get hyperbolic sine, but you always multiply by d by dx of this term over here. Okay, so just think of, so learn the idea, so appreciate the idea, don't memorize a formula. And remember, if a is a function of x, okay, we may need to use the product or quotient rule, okay, depending on the nature of the function. So let me just go through the other results. I won't go through how to get those results. Let me just quote them as they are, and then you can use these steps in order to understand where that result comes from. So fresh page. Let's do this on the reverse. So result number 3, if y equals a hyperbolic tan ux, then dy over dx is a hyperbolic sec squared ux times du over dx. Result number 4, if y equals a hyperbolic cosec ux, then dy over dx is minus a hyperbolic cosec ux hyperbolic cot ux times du over dx. Okay. Result number 5, if y equals a hyperbolic sec ux, then dy over dx is equal to, so I hope you can see that, minus a hyperbolic sec ux hyperbolic tan ux times du over dx. And finally, number 6, if y equals a hyperbolic cot ux, then dy over dx is equal to minus a hyperbolic cosec squared ux times du over dx. Okay, so I didn't go through how these results come to these results over here, so you can do the derivation using the chain rule, using the steps that I've explained previously for these first 2 results. But remember, don't memorize these results, and just one more time, you only use this result if a is a constant. So if a is a function of x, you might need to use either the product or quotient rule. Okay, so that completes this video. I hope you found this video helpful. In the next video, we'll go through some examples of how these results are applied. Thank you.